Welcome everybody to our weekly seminar of Institute of Physics. This week we have a great invited researcher, which is Professor Michael Saliba from University of Stuttgart in Germany. So before our professor start his talk, I would like to introduce him a little bit of his work of field. So Professor Michael Saliba studied mathematics and physics in University of Stuttgart and received his doctorate in Oxford in 2014. He is one of the first scientists ever in field in metal halide perovskites. After his doctorate, he has a postdoctoral research as a Marie Curie Fellow at the École Polytechnique Fédérale of Lausanne in Switzerland. And now he's working in the University of Stuttgart, and he has been head of the Institute of Photovoltaics at the University of Stuttgart. Professor Saliba research focuses in perovskites, a new class of semiconductors that Saliba has played a key role in developing, in which is seen a source of hope for sustainable energy production. Professor Saliba has a H index of 69 and has over that 35,000 sites of his research work. So welcome, Professor Saliba.
Thank you so much, Janani. So I will give the talk now. Is it okay?
Yes, it's okay. Thank you.
Okay, good. So I sent like the message to my group as well, so maybe some of them will join you. Okay, great. Thank you so much. So it's a huge pleasure to have the opportunity to speak here. I'm sorry we didn't manage the last time, so it was quite late here, and so it didn't work out. But this time I'm here, and I'm glad I can share some of my work with you. And feel free also, since this is like a relatively small crowd, if you have any questions, you can also just ask something or put it in the chat. I will try to answer it. Often I will not manage, but if it's possible, I will do it. So
thank you.
Let's jump right into it.
No, it's okay.
Yeah, okay. 1 second. Yeah, here. So let's jump right into it here. Okay. Let's jump right into it. The real heroes of the work are, of course, all the many collaborators that I have the pleasure with working with. So this is the entire institute. We are over 50 people, containing, however, a second professorship taking care of storage, energy storage stories. We have 6 work areas. I'll show them in a second. And we have done historically a lot of work on CIGS, amorphous silicon, crystalline silicon, and now in my person also on perovskites as well. And you can see we have like at least one Mexican student here as well, Jerónimo Rendon. And I was also working with another Mexican for a long time as well, with Silva Turan Cruz. So I have a lot of good experience in that sense. And in fact, before the pandemic, there was also the intention to go to Mexico for one of the Cancun conferences as well. But as you know, COVID has changed everything, unfortunately. I'm also, of course, very grateful to all the other collaborators and most importantly, the money. So we were able to attract a grant by the European Research Council recently. And therefore, we are looking now for PhDs, postdocs, group leaders. So please do drop me a line. I will answer it as well, ASAP, if you have interest, and then we can maybe discuss it. So because this is an online setting, I have 2 locations, actually. One of them is here in the west of Germany, which is the Research Center Jüllich. And then the second location is here, the University of Stuttgart, which is in the southwest. And Stuttgart is very well known for its car industry. So it's the headquarters for Mercedes and Porsche. Every Porsche has the name Stuttgart actually written into it. So if you look into the logo the next time, then you can probably find the name. This is the Institute for Photovoltaics, this part of the building. And we have the photovoltaic panels on the rooftop, of course, as well. And Stuttgart is very famous, as it turns out. I have now the obligation to show you why in the field of perovskites, because the 1978 paper was published from Stuttgart University, as it turns out, from the inorganic chemistry department. So we're very proud and happy about that. Then in terms of our work areas, we have 6 work areas looking into novel materials. That's mainly the perovskites, high efficiency solar cells in the form of tandems, the technology, the sensor properties, and then also the industry upscaling of silicon-based solar cells. And then we have a second completely independent research direction towards energy storage for lithium-ion batteries or water storage, for instance. So just to give a super short overview of perovskites and why they are so interesting. So perovskites are ABX3 materials. They are named after the researcher Perovsky, so it's a Russian name, although Russia is not very popular at the moment. That's from where the origin of the name comes from. And by interchanging one of the, or all three of the components, going from cesium lead trichloride all the way to cesium lead iodide, the entire visible range can be covered from 400 nanometers in the ultraviolet to about 700 nanometers in the red. And even by then mixing parts of tin into the lattice as well, it's possible to go to the near infrared towards 1.1 electron volts, similar, a little higher maybe than silicon-based photovoltaics. And perovskites are interesting because they are low temperature, they are comprised of inexpensive, earth-abundant materials, they are high-quality semiconductors from a solution, and they have a high absorption, which makes them suited for thin films, which can still absorb a high portion of the sunlight, and this makes them very interesting for solar cells and flexibles especially. And then the fabrication is possible in the wet lab instead of a clean room. So this is, I think, what brought perovskites to the table. That made them very interesting. And I will talk plenty about solar cells, but of course, same as silicon. Silicon, in fact, is maybe even more known as a computer chip rather than a solar cell. So semiconductors in principle have more properties than just the one. And in fact, they cover the entire range of optoelectronics. And that's, of course, the case for perovskites as well, going from light emission diodes to single photon sources, which is part of one of our graduate schools that is covering quantum engineering, because single photon emitters from perovskite colloids could be potentially used as qubits for quantum computing. Tunable lasers are being discussed as well, memory effect, high power per weight applications. And here, finally, somebody has found what is on the inside of the Kinder Surprise. It's the violin. So they are useful as X-ray detectors. Then what is, of course, relevant here, you can see it. It took many decades for silicon to reach its peak value, which is now at 26.8%. For perovskites, they've started at 3.8% in 2009, and they've now reached over 25.7%, which is a remarkable journey in an extremely short time. In fact, no other material was able to cover such efficiency gains in such a short time. So it's the fastest learner in history, one may say. And I've stopped counting in 2019, but maybe two points here. Firstly, when I started my PhD in 2010, there was only one publication on perovskites, which was the Miyasaka publication. And then at Oxford, it just popped up in 2011, 2010. And so it was a sensation at the time, but only an internal sensation. And nowadays, it's more than 10 papers per day on this subject. So it's really taken off quite considerably. And I think many, many people are very excited about the research topic. And that's because it has such a remarkable versatility. Then in terms of its history, perovskites, as with everything, new ideas are in old papers or old books. And you see that here in 1893. One of the first publications was here in this German journal written by this American person, H.L. Wells, describing inorganic perovskites in German, which was the language at the time, so it wasn't always English. And then later, you see that here, this is a full paper in Nature, also on the perovskites, fully inorganic still, cesium lead triiodide. That's the full paper, okay? This is how it used to be done in Nature, so you didn't have to do the figures and everything. And then the history continues. Very importantly, Stuttgart University, the first place where MAPBI3, the hybrid perovskites, organic, inorganic, was described as a material group. So the paper was written in German, as it turns out, only the abstract is in English. And many people, therefore, couldn't read it. Also, this journal was only digitalized in about 2013, perhaps. So I had to go to the library and take an actual copy for this paper. And then even if you can take the copy, you still need to be able to read German. So I was in a very fortunate situation, let's say. So most people didn't have access either due to language or due to not going to a library, you know, the place with the books. So it's not very popular maybe sometimes. But funny enough, most people have now access to the paper and also seem to have improved their German skills a lot as well. So the paper now is very well cited after 40 years. And I think this is beautiful because it shows that basic research, you never know when it comes to the front. So when Dieter Weber published this work, he didn't know this would happen. I think that's a nice story as well. It's not all about maybe the numbers. It's also about doing good research, and then time will decide how important it will become. And this definitely is one of the highlights, I would say. So perovskites are easy to make. This is a video that we took in Oxford back in the days. You take the perovskite ink, you spin coat it, and that's it. So this film, which you'll see in a second, when contacted correctly, is a solar cell. So it's very accessible. The feedback cycles to make a solar cell from bottom to top takes only about a day, 2 days, unlike 3-5 semiconductors or silicon that can take in a lab fabrication scale many weeks even. And so I think this also enabled many groups to have like a low investment in terms of like starting up the research as well. And therefore, you can see it like many groups from all over the world started to move into it. So then 2 big directions. One is flexibles. As mentioned, it's a direct semiconductor, so it's suitable for flexible substrates and roll-to-roll processing, for instance. The second big direction is, of course, to try to assist silicon that is now covering the market with 95% by putting a perovskite silicon tandem. The perovskite layer can filter out the blue light, turn it into electricity without much internal thermal conversion. And then the silicon can take care of the red part of the sunlight, turning it very efficiently because, again, little internal thermal conversion into electricity. So you can double dip into the sun spectrum that way. And because they assist each other, it's called a tandem. So then now the rest of the talk, the main focus will be on solar cells. Just to be super upfront about it as well, you see that here, the perovskites, they are sandwiched between an electron transporting layer, which is fluorine-doped tin oxide with a compact layer, and a little bit of mesoporous TiO2, a remnant of the history from the dye-sensitized solar cells. And then the top layer is a Hall transporter, commonly a small molecule like spiromethan, but it can be other stuff as well, like copper thiocyanate and so on. And then, of course, you need to contact it, in this case, with a metal electrode. So then, this is the messiness of the electron microscope. So schematically, you have the active layer, and then it's sandwiched between an electron and a Hall transporter. That's how the basic perovskite cell is working. So now, one of the big research questions that I've pursued for many years now is to look into the phase stability of perovskites. And this is sort of the perovskite structure. It's octaedra that touch each other. So it's a 3-dimensional network. In the center of the octaedron, you have lead or tin. It's a metal position for a divalent metal. And then in the corners of the structure, you have iodine or bromine or chlorine. So it's a halide. That's also why they are called metal halide perovskites. And then these octaedra, when put together, they leave a gap, the cation gap. And this cation doesn't interact much with the metal halides, which is very interesting. There's a little bit of interaction, but it means essentially you need something in this gap so that the metal halide octahedra don't collapse. And when you make it too big, there is no more space. When you make them too small, there is too much space. So you need to have the right situation. And geometrically, you can, of course, describe this. So if all the spheres were to touch each other in this 3-component system, you would get to a relationship like this one here. Ra plus Rb divided by the square root of 2 plus Rb plus Ri. And a tolerance factor, that's what it's called, of 1 means that all the spheres are touching each other. And you can see it must be geometrical from this square root of 2. And this is a well-known geometric measure for determining whether the structure will be phase stable afterwards. So a tolerance factor between 0.8 and 1.0 leaves a gap for the cation. If we fix the lead and the iodine, because that's beneficial for the band gap, it leaves a gap of 1.6 up to 2.6 angstrom. Okay, and if any component that has this kind of size fits into this cation position very well and stabilizes it there too. So schematically, it looks like this. Empirically, we know that that's the condition for photostability. A tolerance factor of 0.9 gives only a black phase. Unfortunately, at 0.8 and 1.0, there's polymorphism, the coexistence of multiple phases. In the case of perovskite, it's an alpha and a delta phase. The delta phase, because it looks yellow, is also called the yellow phase. And the alpha phase, you see that here is the black phase. So that's what we call it in literature. And this example of cesium lead triiodide exemplifies that the yellow phase, which is a very bad absorber, is what you get at room temperature, and only when you go up in temperature you get the black phase. So how to avoid that? How do we suppress this yellow phase temperature? How do we stabilize the perovskites in their black phase at room temperature? That's one of the guiding questions for the next couple of slides. So let's look at it more systematically. Here on the y-axis, you see the tolerance factor. Only 0.8 and 1.0 give a stable structure if we fix the lead and the iodine. And then on the x-axis, we have different cations and their radii. And you can see here the alkali metals, they are obvious targets. Cesium, for example, is well known, methylammonium and formamidinium. These are the only ones that are suitable for this tolerance factor relationship. All the others don't fit. So if you know any cation which could fit in the in-between spaces, I'd be very curious. So I didn't know of any of them. So I was looking very hard throughout my PhD and postdoc time as well, but I couldn't find any of them. So for lack of finding them, in literature, people then started to mix the cations together in order to get like an average, which is in between, in order to find the sweet spot where you can use multiple cations together in order to have a good tolerance factor, but also a good composition, because some of these components like methylammonium may be unstable. Formamidinium is relatively bulky, so you want to sort of be able to move along this line. Of course, if there were atoms which were slightly larger than cesium, that's what you'd do, but unfortunately they don't exist. So you had to go towards the small molecules, and then the larger molecules like imidazolium, ethylamine, and guanidinium are not suitable either. So this was sort of from where we started. And the question then is, how do we move on from here? How do we turn this into a concept? And so the idea was to use all three together as a triple cation approach to treat these three cations described in literature as space vectors and to linearly combine them. And the consequence would be the triple cation, which wasn't described in literature then, a quadruple by using a slightly smaller cation compared to cesium, and then slightly larger cations compared to formamidinium, to use this mixing and alloying approach rigorously. So this is sort of the roadmap. And how did that go? So first of all, in 2015 already, or 16, when this work started, it was already very clear that practically all the perovskites there are, so this is from the NREL chart just taken this morning, from all the perovskites they are lead-based, they're using mixtures of bromine and iodine, anti-solvents as well, and mixtures of methylammonium, formamidinium. So it was interesting that these double cation perovskites were leading in the community. They're still leading in many other ways as well. And when you look at these like extremely high-performing perovskites with MA and FA in the cation position, it's still very apparent that they have this delta or yellow phase as an impurity. And I thought it was very curious. So although these materials are leading, they are still full of impurities. So if you are from the silicon community or the 3-5s, this is a very strange thing to observe. So one idea was to say, well, since they are working very well, can we tweak them a little bit by adding small bits of cesium, for example, in order to get rid of the delta phase, because it's an example of the polymorphism that I've alluded to earlier. So by adding systematically larger amounts of cesium, all of a sudden the delta phase disappears, and even the lead iodide excess is eaten up as well. So the material seemingly has now like a much higher crystalline quality with this beautiful perovskite peak at about 14 degree. So then in terms of the UV vis, it was interesting as well. It was a completely different formation dynamics as well. So when MAFA is used, it needs an annealing step at 100 degrees for 40 minutes. So you have no chance to form the black phase without heating. However, upon adding cesium, all of a sudden the material would form black without any annealing whatsoever. So we took XRD of this wet film, both here and in this case, and it shows very clearly that these double cation perovskites, they form from very random phases. So this kind of thing must turn into this one, and this introduces a lot of variability. I think that's the deeper reason, which I believe is now confirmed in literature as well, why these double cation perovskites are not very easy to reproduce for many groups. Whereas when small amounts of cesium are put in there, all of a sudden, all of this variability is bypassed. The material, because of seeded crystallization, starts from the correct perovskite phase from the get-go. Of course, we still have a lot of solvent in here, but it was very clear that this is a completely different film formation before the annealing is started. So that's what you see here, these triple cations. And the hypothesis was that MAFA-based perovskites are much more sensitive compared to the triple cations, which increase the reproducibility by being insensitive, so to speak, to the environmental conditions. And we made like so we took this to its logical conclusion. We even tried to make solar cells without the annealing step, and indeed we were able to show that without any annealing whatsoever, still our solar cells would work as a kind of solar pane concept. Very interesting. It was a lot of fun at the time. And here you see also the cross-section of these double cation perovskites. Not only do they form the final phase after annealing, but also their grain structure is very different as well. The grains are ragged. They are stacked on top of each other. You have internal grain boundaries. So it's a bit of a mess, actually. Whereas when cesium is used here, you see it in the zoom out much more clearly as well. You have so-called columnar growth, where the grain goes from top to bottom. Very similar maybe to multicrystalline silicon as well. So quite different situation. And the sensitivity hypothesis was also proven here. We had a lot of variability when analyzing the MAFA perovskites. Even here we had like devices that went as low as 10%, but people usually don't report on them. So this is the problem sometimes. And then only 18% was the maximum we could reach. But then upon adding the cesium, all of a sudden our baseline started off at 17% with top values towards 21%. And it was very interesting because at the time, one of the reviewers also asked us to demonstrate by more than one person. So we put another 2 people on it, and they could indeed show that they can also reach 20% now as well, confirming, I think, very nicely our reproducibility. So we're very, very grateful to the reviewer, although it didn't feel like that at the moment. And here you see also a stabilized power output of 21.1% with very little to no hysteresis. We also saw long-term stability for 250 hours at 18%. And we also discovered, and the subsequent work was written on this, that there's an initial loss component which can be recovered later on as well upon resting the device in the dark. And if you're interested in how to make these solar cells reproducibility and increase them, you can see that here. It took us many, many batches. These are all the device data that we've recorded. And I think in the future, it will be more and more important to record all the small detailed steps as well. So here, this is about 20, 30 pages on the protocol, how we made these over many years and many, many people as well. So how do we continue from the triple cation? And it's always important to read the paper right to the end. So the last sentence of my conclusion reads, this work also opens the prospect for all the other alkali metals, including potassium and rubidium, to be explored for the multi-cation approach as a novel compositional strategy. And the alkali metals were chosen specifically because they are +1 stable, but at the same time, I didn't know of any atom larger than cesium and +1 stable. And so then the next logical situation would be, of course, to go down in the periodic system. You could say, okay, there is francium. That's true. Francium is also larger than cesium, but it's radioactive. So that wasn't really an option. Although if you were to take francium, radioactive atom, nobody would talk about the lead toxicity anymore. So that could be a kind of advantage. And you see here, as predicted, only the cesium has a black face, albeit at high temperature, and the rubidium never has a black face at all, no matter at which temperature. So then the idea was, since our mixing approach previously was working extremely well for us, how about using small amounts of rubidium in this kind of mixing approach? But then how do we mix? So I always wanted to keep formamidinium because it's a high temperature stable and it's causing the most redshifted band gap without using tin yet. So formamidinium was a given. But then let's say the next situation is to add methylammonium. But also methylammonium is forming a nice MaPbI3 perovskite. So there's that possibility, MaPbI3, FaPbI3. And if I mix them, I have a double cation perovskite. So that's clear as well. 3 components, I discussed it, clear as well. I have a triple, 3 double possibilities, and 3 single possibilities as well. And then with the 4 components, I mean, naively, we were writing these down. So all of a sudden, there's a quadruple, 4 triple embodiments. It's all in the supplementary information of this paper. And there are 4 single possibilities as well. And this was curious. So I saw that from sort of the rear view mirror in a way, that something was going on here. But so interestingly, the triple and the quadruple worked well. So keep this figure in mind. I'll show it later again. And it also gave us, I'll keep the story short, a stabilized power output of 21.6%, very high voltage of 1.24 volts compared to like a conservatively estimated band gap of 1.63, showing a loss in potential, which is the difference between band gap and VOC, of about 400 millielectron volts, which is comparable to silicon. And this also highlights that perovskites are closer to gallium arsenide, which is a top performer for solar cells. And also this means automatically a high voltage means high electroluminescence, something you see here in this video. This is also the stability holder. And already at ambient light conditions, the solar cell is very beautiful, showing LED behavior. And this is not even optimized yet. The layers are still too thick. There's a lot of self-absorption, and the contacts are not optimized either for LEDs. But still, it shows very clearly this is an extremely efficient semiconductor with very little non-radiative recombination. Practically all the recombination is radiative in this case, the kind of stuff that you know from in the Shockley-Queisser limit. Here you see a close-up. Very nice. Okay, stability, of course, one of the big concerns. So here, two directions of thoughts entered, two different strands. First, we discovered that the spiroometard hole transporter was permeable to metal transport upon heating. Okay, so this means although the perovskite may be stable, the surrounding layers could cause a problem. Second work here, by using a polymeric hole transporter, although it didn't give high numbers, it was clear that it hampers the metal transport. So it cannot leak into the perovskite layer, destroying it. So then this gave the idea of combining the best performing perovskite at the time, which was the rubidium-based perovskite, together with a high performance polymeric hole transporter. And that gave us enormously high stability at the time, at 85 degrees under full illumination without the UV part although, and at max power point, which is more than what the official stability standards of industry require. There you don't need any light, but it's very boring to measure them in the dark. So we wanted to see something. And for over 500 hours, only 5% of degradation. Highlighting that ultimately, if you want to know why your device is not stable, you need to look at all the different layers, the hole transporter, but also the perovskite itself as well. And I think this will be key for the future development as well, to look at all the different layers. And I made this point also in this overview here, that in the future we need established stability protocols similar to what we do with maximum power point and JV curves in order to be able to compare the data with other laboratories in the future. So a kind of stability task force, a worldwide one, will be required. And it will also have to take into account the idiosyncrasies of perovskites. So for once, people need to think of this dark recovery. When a device is run at maximum power point and it's perovskites, it may recover and retrieve its initial burn-in effect. And that's a peculiar detail which is only seen in this form for perovskites. And that's exactly what the new stability protocols need to take into account. Each material has a special weakness or maybe even a special strength, and the protocol needs to know about that. For amorphous silicon, it's the Stabler-Wronski instability, the dangling bonds which are saturated by hydrogen and which sort of re-emerge upon running the device. So that's why you need a lot of light soaking. And so the stability protocols for amorphous silicon take that idiosyncrasy into account. We must do the same for perovskites as well. We must find its weakness and use it as an acceleration factor for stability. So I think this will be very key for industrial deployment. And this also was written down beautifully by Mark Kenkin and Monica Lira-Cantu, where many labs together also made this point in a more comprehensive form with very detailed advice on how to measure stability in the future as a research community in this ESOS procedure. Okay, then here you can see Silva Turan Cruz, a fellow Mexican student who was with me at the time. And there we considered, although we made such a complicated perovskite with like 4 cations, it still contains methylammonium, which is a risk factor because it can easily decompose in a thin film, for instance. At the same time, also, we're using large amounts of bromine. Although it's only 17%, it's large in the sense that the metal halide position is very responsible for the band gap. So 17% shifts the band gap by quite a lot, whereas the cation position doesn't. So the target was to remove methylammonium for stability reasons and bromine for band gap reasons. And here on this Shockley quasar graph, essentially what we tried to establish was Fa-PbI3 only using rubidium and cesium. No unstable methylammonium, no bromine in order to stabilize the yellow phase. Only rubidium and cesium iodide. So we worked on that rigorously. Here we have some figures where we mixed the cesium Fa together, the rubidium cesium as well, and we found that only a mixture of the two, rubidium and cesium together with Fa, has both the morphology advantages, but also the advantage of high performance ultimately as well, with a low band gap at 1.53. And you see that here, we started making planar devices, which are very hard to make because you don't have the advantage of the mesoporous structure underneath. It required us to use PMMA and PCBM PMMA as a passivation at both top and bottom interface. And they were necessary both for performance reasons in order to avoid pinholes, here, for example, many pinholes, but also for stability reasons ultimately as well. And beautifully, it also confirmed here that we had high currents towards 25 milliamps. And nowadays, it's nearly 26 milliamps per square centimeter using pure Fa-PbI3 with similar approaches to what we've presented here. Now, sometimes people ask, why not simply use cesium Fa? And we tried very hard, actually. It turns out, however, only when we use rubidium, we can get reproducible data. So it seems you either need a triple cation comprised of rubidium cesium Fa or rubidium cesium Ma or Ma cesium Fa. So this is what you require. And why is that? So there was a follow-up work by Seidmaninov and Sargent in 2020, and they showed in the precursor that the double cation perovskite cesium Fa, that is, upon exposure to chloroform, that's an antisolvent, form wide band gap contaminants, whereas the triple cation, both in its cesium Ma and in its rubidium cesium version, they don't have this wide band gap contamination. So the hypothesis is, why is cesium Fa less reproducible? Because it forms tiny bits of wide band gap materials during the formation process. And that's what, in the end, harms you when the perovskite is formed. That's something that also Aram Amasyan in 2019 showed the rubidium was necessary to form the black phase with as little yellow phase impurities as possible. Now, the top layer for the polymer, the PMMA, we tested why that is working. And in the end, we found that the insulating PMMA is going into the cracks of the perovskite. You see that here, insulating it, and therefore preventing shunting. And we also wanted to investigate the bottom interface, but we didn't have an idea how to investigate the bottom interface because it's buried. So if you have ideas, please let me know. Yeah, and also people now say, is it over for MA-PbI3? I think it's an interesting scientific question. As a company, of course, can you stick to methylammonium when you know it's volatile? That's for your pocket to decide and for your checkbook. I'm not sure. We have presented an alternative to methylammonium using rubidium cesium Fa, but nevertheless, here a very nice study by Anita Hobeli shows by using gas chromatography that when correctly encapsulated, even MA may survive in the long run as well. So this will be very interesting to see. And we also had a follow-up on that as well here, where using polymeric layers, so this was one of my former master students who's now at Oxford doing very well there with Henry Snaith. By using PMMA at the top, we could see that the stability of MA is improved actually. So that will be an interesting story. Whether or not it's enough for the next 25 years is something that will be investigated. So this brings me to my last point in this segment. So I talked about mixing with smaller cations with rubidium and cesium, for example, but also it's of course possible to mix with larger cations as well. And we tested guanidinium, ethylammonium, and imidazolium, and we found with theory from Filippo De Angelis that only ethylammonium, because of its mischaracterized cationic radius, so it's smaller than literature assumed previously, that only ethylamine can successfully be mixed with methylammonium. You see that here, and it shifts beautifully the band gap through the green, which is exactly the area that is important for display technology. So we made devices from it. All of them worked very nicely, also up to 50%, showing that ethylammonium of the larger cations really forms like an exceptional case. So this could be a good direction, and I think Nangju Park worked on very closely as well. So then people ask, where will this all end? We have now the 4 cations, even ethylammonium. And remember, I had like the sketch before where I said, this is interesting how the combinations line up. That's something I dubbed the perovskite genome project. You see that here. These are all the literature results on the different cations, on different metals and halides which are reported. And combinatorially speaking, we have over 651 candidate compounds by combining all of these. And by keeping formamidinium, for example, this is what I've done previously, I could reduce the experimental parameter space further. But how did I come up with this formula? Why is it exponential? It's something you see here. Remember that something interesting was going on. I told you, keep it in mind. 1, 3, 3, 1, 1, 4, 6, 4, 1. So that's oddly familiar. It's this formula here, M choose K. So you see it here. It's the so-called Pascal triangle. And you may know it still from the formula a plus b to the power of n. Okay, a plus b to the power of 2 is a squared plus 2ab plus b squared. That's the formula here. And this 2 is also capturing combinatorics as well. That's what you see here, 2 single cations, 1 double cation. And okay, the empty choice I don't take into account. And here, 3 single cations, that's the 3. 3 double cations, that's the other 3. 1 triple, and so forth. 1 quadruple, 4 triple, 6 double, 4 single. That's exactly what this formula is reproducing. So it's the combinatorics of it. And it's increasing the Pascal triangle with the power of n. So it's exponential. That's how I came up with the formula. And by putting all of these together, all of a sudden, the experimental parameter space is relatively wide. Even when fixing the formamidinium for band gap and stability reasons, I end up with 32 compositions. And I didn't even put the permutation into the halide position. So triple halide are also used now as well. And so this is interesting. So this gives us something that I call the polyelemental perovskite library, which could be maybe a future concept as well. Here you see a speciality. If we say MA free, or if you want to go fully inorganic, you can then select it. And then I thought, what if we were to go really crazy, and it's in the supplementary of this paper, I'm not showing it here, by adding all the components that are reported in literature, cobalt, europium, samarium, everything there is in the periodic system, which has even a tenuous link to the perovskites, I can write down a list with over 40,000 compositions. And that's something that is in the supplementary of this paper here. It's very exciting, actually. So I really had to use the maximum of the computational power at the time, because I'm not a good programmer. And then how do we use all these perovskites and form thin films from them? That's something you see here. We had, this is a work I did during my PhD at Oxford. You can see here by using a step annealing. Remember, we need annealing for the perovskites. I used like a gradient. So I had to go to the hot plate every 5 minutes to heat up by, I think, 5 degrees. So it was a bit of a painful process. And then at the end, I introduced a flash annealing for 5 minutes at 130 degrees using GWAX, but also SEM. It was clear that the flash annealing creates a lot of texture. So the heating creates structure in the perovskite. That's the point of these publications. So by using the hot plate in a creative way, I can control how the grains are lining up. This is sort of something that stayed with me at EPFL later, and then also in Fribourg, where I did my group leadership. And you can see here with Sandy Sanchez, who was a PhD with me at the time, when we introduced a halogen lamp here, like a very short light burst with a halogen lamp. It's also known as rapid thermal annealing in literature. We gave it a new name. We called it FIRA, flash infrared annealing. People always give new names to old concepts. We found that the morphology can be very well controlled. And this is a very, let's say, sophisticated way of controlling the heat budget on the perovskite sample. So what I've shown earlier here, by manipulating the gradient and then to introduce a flash annealing, can of course be done very nicely with a lamp. I can control its intensity, how often I shine in. And so now all of a sudden, instead of using the crude instrument of the hot plate, I'm using a precision scalpel where I can tune very nicely the heating behavior. Something you see here, completely different grains compared to the anti-solvent process. There's a video as well, just to make it clear how this looks like when the wet film turns into perovskite clusters. 1 second. That's how it works. And then using the flash annealing, we can control it. It was a bit of a painful job, but it can be done. And then we played around with this idea. It was a lot of fun. So we put so this is Antonio Günzler, who was also a PhD at the time. And we put like gold points on an FDO substrate. And the gold chemically reacts with the perovskite precursor. Okay, so of course, having gold inside of a solar cell in the active layer is a bad thing. I know that. But we wanted to prove the point that it can be used to control the grains. Because the oversaturated perovskite thin film, when it's wet, it agglomerates around the gold points, and then it forms a nucleation seed. And this seed crystallizes according to the pattern that we have written into the structure, something you see here. And in the end, the grains come out perfectly hexagonal, similar to what we have put at the very beginning. That's interesting because usually solution processing is a random process, but in this case, it gave us the beautiful shape of these hexagons here. You can see this in this video. We also use this far infrared annealing. You see how the grains grow within a very short time just by exposing them to this infrared annealing step. And maybe by insulating these spheres in the future, or maybe we can induce this mechanism a little differently, this can be a way to control the crystallization. So although we are short on time, let me show you, apart from solar cells, something else in order to highlight how versatile this material group is. What can absorb very well can also emit very well. We know this sentence, especially when it's a direct band gap semiconductor, the radiative recombination is extremely high. So it means the material is also very shiny when operated in reverse mode compared to the solar cell. And one very famous, of course, optoelectronic device is a laser or an LED. And those require at least the laser optical cavities. So a famous optical cavity is, of course, the Fabry-Perot, where you have mirrors in a certain distance. Another one, also extremely well known, is to use alternating different indices of refraction in order to induce a standing wave. And that means backscattering. And that means the optical cavity is written into the material by structuring it. And why is that used? Because it's mirror-free, scalable, and compatible with industry. So distributed feedback or distributed Bragg reflectors, very well known for lasers as well. And you see here the basic thinking behind it. This is the Bragg condition for orthogonal pumping when the sign is 90 degree or pi half. And you see here, if we use m equals 2, so this is a second order surface emitting mode. It's a bit difficult to do an edge emitting mode. We have the periodicity here, lambda, and then we need to have like an effective index of refraction. See that here? And doing a back of the envelope calculation with the perovskites we could do at the time at 780 nanometers and an effective refractive index of 2, so it's just a geometrical average. The corrugation of the structure needs to be about 400 nanometers, 390. Because I'm not a theoretician in this way, this was only back of the envelope. We used all the different corrugations between 370 and 450 nanometers. Here we ran out of beam time. Okay, so then this became the test stamp. Here we had to take it out, unfortunately. It took a long time to make the stamp. And so we used the stamp and we put it on a polymer with nano imprinting. So this is the first nano imprinted sample we saw. Still not very perfect, but it worked nicely. You can see the interference fringes. And then on the polymer, unfortunately, we cannot deposit the perovskite directly because it's dissolved in DMSO, which in turn would dissolve the polymer as well. So instead, we decided to evaporate the perovskite here. You see that here. And here, when we perfected our method of imprinting the stamp, the perovskite indeed, you can see it here, is directly on top of the stamp. And why do we evaporate? In order to inherit the pattern underneath. You see that here, perfect pattern sort of inheritance. And here, this is the test stamp. Okay, this is where I called it the test stamp. This is where the pixel stopped from the e-beam time. And did it work? When we pumped this electrically would be the dream. when we pump it optically, what happens. So we use the pump at 530 nanometers, well above the band gap. You can see how the superlinear behavior shows up all of a sudden very nicely. And this also showed that by structuring the perovskite into a DFB structure, distributed feedback, it becomes a lasing material as well. And I think this is one of the big directions for many groups as well. This can be interesting for lasing, but also for superfluorescent LEDs as well. And this, I think, is a nice point to finish it. I'd like to thank you for your kind attention. I'm very happy to hear your questions as well now. Thank you.
Thank you, Professor Saliba, for your presentations. We have a few time for questions. So any questions from the public? Okay, go ahead, Jorge Luis.
Okay.
Hello. I have a question about the additive engineering. What do you think about it?
That's your question? What do I think of the additive engineering?
Yes, it's a question about your opinion, and if there is something like, how do I say it, in such as an improvement using the additive engineering and no like the cationic interchange.
Well, I think it's a nice direction, the additive engineering, because it's usually very difficult to manipulate a semiconductor because most of them are grown from the vapor, let's say, or from like PVD perhaps. And this is a possibility to manipulate. The additive engineering, why did it become so important? Maybe that's another way to look at it. I think the reason is because you need to stabilize the yellow phase of Fa-PbI3. So if you ask me, I think everything that people have done in the last perhaps 8 years is to crystallize Fa-PbI3. Me too. What I call the triple cation in reality is only 17% of cesium. No, even less, 5% of cesium, 17% of methylammonium, and 83% is formamidinium. So we should stop pretending in a way. We are only interested in Fa-PbI3. And for that, we manipulate it with additives, we manipulate it with heat, we try to, we try to threaten Fa-PbI3, we beg it to turn black, we do everything we can to talk it into being black, right? And that's what the additive engineering is all there is. So we should be honest with what we're doing, which is to crystallize Fa-PbI3. And I think that's the main purpose of additive engineering. Even for me, when I write all these millions of possible combinations, in the end, it all comes down to crystallizing Fa-PbI3. And why is that? Because Fa is the most redshifted perovskite there is, and because it's thermally more stable than the others. And so also the thiocyanate, it's the same thing. Formate, it's the same thing. And I think we can even see it from the FIRA method, the far infrared annealing. If we use heating in a different way, the Fa-PbI3 also turns black for a longer time. And so maybe in the long run, we will find a different way to stabilize the Fa-PbI3. But I believe the additive engineering will be alive for as long as the Fa is not black at room temperature.
Yeah, I completely agree with that, because making the cationic interchange, I think it's a lot of work, and working with an additive, I think it's a possible and economic source to make the black phase without making the cationic interchange.
Yeah.
So that's what I think.
Okay, great. Yeah, thanks. Nice. It'll be interesting for me, of course, to see as well where it'll end. I mean, we never wanted to mix all these different additives, but this is what the science gave us.
Yes, no, it's impressive, your work. Thanks. Thank you a lot for the.
Thank you. Thanks for your question.
Thank you. Any other questions from the public? I do have a question. All the perovskites that are the top of the power conversion is made under very controlled conditions, like under the glove box. Do you think that we will be able to create a perovskite solar cell without that glove box?
I think we not only should we must ultimately.
Yeah.
I think already if you have like cesium, like triple cation with an increased amount of cesium, they are much more robust against outside conditions. I think we must find ways to increase the processing corridor for various reasons. I mean, it's obvious for industry, but also for research. It's a very bad research direction if only some people can make it. This means the processing corridor is very small. There should be no secret for the perovskite. Everybody should be able to make the perovskite like you do ALD layers now. You know, ALD used to be very difficult. Only maybe a few experts can do it. And now you can simply buy a machine that does it for you. So what used to be a Nobel Prize, ALD, let's say, is now simply a product you buy. And this must be the case for perovskites in the long run as well. It's not acceptable that it's so difficult to make at the moment. And I think we need to find additives which robustify it against the atmosphere. That's one aspect. But also maybe we need to find processing methods which don't allow the perovskite to react very sensitively to the environment. For example, the FIRA method can be used outside because it's only 2 seconds long. So the perovskite doesn't have time to think what's going on. And this, we need to shock it in a way. And it's the same for many other technologies as well. And because it is my opinion, it's exactly because I believe there is a corridor for perovskites to function outside that inside of the glove box solutions will not make it. So a competitor that tries to outcompete perovskites which are made in the glove box, I think has a viable chance. And because of that, they will win. So if your product requires a glove box, I think you're in a bad position already. Lithium-ion batteries. So there you need the argon glove box, I agree. But that's because of the science. I don't see a scientific reason why the perovskites cannot work under, let's say, air-conditioned conditions.
Yeah. Thank you, Dr. Saliba. Any other question from the public? So
Yeah,
thank you.
I have a question.
Go on,
Sorry.
Marisol.
Nice to meet you, Dr. Saliba. Nice presentation. I have a question about the technique evaporation. How you talk about some of this technique, please? How do you think about the evaporate single crystals?
I think the evaporation is extremely well established. LEDs, OLEDs are using them, for instance, and they are very reproducible. So most likely perovskites from solution processing, if you find a good composition or something like that, will be good candidate materials for an evaporation chamber in the long run. Evaporating a single crystal, you mean like a monocrystalline layer? Is that true? Is that what you mean, Marisol?
Yeah, I was thinking about single crystals like a precursor in the evaporation.
You wanna okay. So you want to put the perovskite into the crucible and then evaporate it.
Exactly.
Yeah, I think there are some publications in it. It's a good idea. Sorry, could you turn off the microphone? It's always irritating to hear your own voice, actually. I think it's a good idea because when the perovskite is completely formed, its sort of melting point, its evaporation point changes as well. So, for instance, mechanical synthesis gives perovskites by mechanically synthesizing with a ball mill. And then when putting it into the solvent, the solubility is changed compared to putting the individual components into the solvent. And I think sort of evaporating a single crystal or perovskite powder, which is sort of also perovskite in the end, will be a much easier to control process compared to co-evaporation of 5 or 6 different materials. I mean, our institute has also pioneered the CIGS in the 1980s, not with me, my predecessor, but they used 6, 7, 8 sources, which is insane. Each source has its own gas pressure, and also the organic components are very difficult to control. So I think the idea of evaporating the crystal could be really a solution. You should try.
Okay, thanks.
Thank you, Marisol. Any other question? I think we don't have more questions. So thank you again, Professor Saliba, for your presentation in our weekly seminar. And maybe a few of the people present here will write to you.
Sure, yeah, I'd be happy. Yeah, great.
So thank you so much for your presentation, and I hope we could see you here in Mexico in the
Me too.
MRS Congress the next year.
Yeah, that'd be great. Thank you so much for having me. It was a pleasure. Have a good day.
Have a good day, everyone. Thank you.
Thank you. Ciao, ciao.
Thank you.
Yeah. Gracias. No, gracias. It's Mexico.
Yeah.
No TH.